So good evening, guys. Today we are going to cover the part related to reinforcement learning. Okay, from a machine learning, we are having three types: supervised, unsupervised, and reinforcement. In that, we are going to cover the things related to reinforcement today. So here it works as a like agent environment structure is there, right? And it learns through the like reward and punishment thing, and purpose is to maximize the rewards. Okay, so suppose robot navigation is there, energy optimization, uh, autonomous car. These are some of the examples for the reinforcement learning. What actually it means? So it's a machine learning algorithm where agent learns by interacting with the environment. Simple example: suppose robot is the agent, and whatever surrounding is there, that is called as the environment in which environment it is moving. Suppose autonomous car is there, so that car is a agent, and whatever things are outside it, that will be coming under the environment. So agent receives the rewards. What it receive? Agent receive the rewards or penalties based on its action. What is meant by reward and what is meant by penalty? Suppose for each correct action, it will receive obviously reward. If empty road is there, agent or like car should apply like accelerator. If obstacle is there, brake should be applied. If turn is there, steering should be revolved, right? So these are the like correct action, so there it will have a reward. If there is incorrect action or mistake is there, if there is obstacle and still it is pressing a accelerator, so that will coming under the penalties. Yes, are you getting these two things, reward and penalty? So this will be something, or like more or less it will be a trial error thing. Through the trial and error it will learn and it will follow that path. So maximum cumulative reward is the goal. What is the purpose? Purpose is to accumulate maximum number of rewards over the time, and learning will be through trial and error process. Learning will be through trial and error. So agent improves its decision making. Agent improves its decision making using a feedback from the environment, and commonly used in a robotics, gaming, and self-driving car. So these are some of the examples or applications for this reinforcement. So this is one of the what we can say, one of the machine learning technique there, and these are some of the key components for the reinforcement learning. For example, agent is there. First thing, agent, that is the learner or a decision maker in a system which takes the action to achieve a goal. Suppose agent or like a robot is moving from certain location or destination. So this is start point, this is end point. So it will follow some path. So that path will be a shortest one. It will try to find out that shortest path without having any like clashes. So it will find the optimum path in a minimum time, shortest path without having a clashes or without like disturbing anything. So that will be the like goal. That will be a goal, and that will have like actions. So robot, self-driving cars, whatever we are using in a game AI, game artificial intelligence, those are some examples for the agent. Then environment is an external system around a agent with which agent is interacting. So environment responds to the agent's action. For example, in case of a autonomous car, road is there. In case of a game board is there. Real world surrounding, whatever surrounding is there in a like industry premises for a robot, that is the environment. And these three things are important now. State, action, and reward is there. State, action, and reward. What is mean by state? So it represents the current situation. In which position, at which position right now the agent is. So that state is defined as a current situation of the environment, which helps the agent to understand its position and condition. Okay, so you will see this part in implementation. We will cover this thoroughly in a implementation part. What is a state? So that current location of a robot, suppose for example, this is the current location, this is the next location, then this is the current location, this is the next location. Though this next position depend on the last position, this next position is depend on the last position. Like this, it will have the like relationship between the current and previous position only. And whatever actions or operations are there, whether it is moving a left, whether it is moving a right, whether it is like stopping the things, brakes are applied, accelerator is applied, that operations or decisions are taken by the agent. Different actions will produce the different outcomes. So that is known as the actions there. Okay. And reward, that is a feedback. So if there is a correct action, you will receive the positive feedback. Positive reward encourages the good action. If it is like mistake or like negative reward, that will discourage the wrong action. So example, that is a winning a game, give the positive reward. Okay. So whatever feedback we are receiving, that is a reward. So this state, then action, and this reward are the three key components, important one in a reinforcement learning. And the strategy that is followed, process that is followed by the agent to select action, that is known as the policy, which define what action to take in a particular state. In which direction you are moving, that agent is moving left, right, or like up, down, like that. And value function measures how good a particular state or action is, and it helps the agent to maximize the future rewards. And ultimate aim is to maximize the rewards only, to maximize the future rewards only. Is it okay, guys? Are you like comfortable with these terms? Yes, any doubt?
Yes, sir.
Yes, sir.
Okay, good. So this is how just a system will work there for reinforcement learning workflow. Like it will observe the environment, agent observe the environment, that is a current state, we just call it as a EST, that is at time t of the environment. It will select the action, in which action in that particular state, which action should be taken. So in order to move the robot, suppose the your ultimate aim is this. So in which direction it will move first, right, or like up direction, or like down direction, that way, based on its current policy. It will perform the action, selected action is executed in the environment, and it will like receive the reward if it is action is correct, and or a penalty if action is wrong as a feedback. So that feedback is like R, this is A, and this is yes. So SAR define these things. If agent update its knowledge or a policy using a reward to the next state. If it is like a correct action, it will receive the positive reward. If it is a wrong action, it will receive the negative reward. And those rewards will be collected cumulatively in order to like reach the destination. So the process repeats that for the next state, like next timestamp is t plus 1 until the goal is achieved. T plus 1, t plus 2, t plus 3, these actions will be there, but there will be relationship between the simultaneous one, t plus 1 and t plus 3, like that. So sorry, t plus 1 and t plus 2 only. This is how it will work. So these are some of the methods which are under their reinforcement learning. If we are using this generalized term only, it's fine. Reinforcement learning is like alone sufficient. So some are the like model based learning is there, model based reinforcement that we are generally using, right? So examples are like DynaQ or like word models, or IT I2A is there. Model that is a free reinforcement learning. Again, there is a agent, action, reward, and environment there. So that is Q learning algorithm is there that we are going to implement today. SASA is there, reinforcement learning is there. So the agent learns a policy or a value function directly from the interaction with the building an explicit model in the environment. So when there is a direct relationship between the agent and environment, that type of learning is called as the model free reinforcement learning. And this value based model is nothing but learn the value function that estimate how good a state is or how the state action pair is. So expectation is like maximize the cumulative reward. So if wrong action there, suppose this is like destination, so this will receive the positive reward. If there is a wrong destination, the robot has reached, then negative reward will be there. So maximum number of iterations will be there. Deep Q network is there. Deep like Q learning algorithms are there. Different algorithms are there. If it's a policy based method, so it will learn a policy that will map from the state to action directly without estimating the value function. So the goal is to find the best policy that maximizes the expected cumulative reward. What is the goal? Reward should be a maximum one as per the state and action, and cumulative reward, that summation should be a maximum one. So examples for that is like reinforced policy gradient, PPO, A2C, TRPO, different algorithms are there. We are not going to focus on all these things. We are just going to use it for the Q learning. Okay, for robot movement, we will see the implementation. deep reinforcement learning model is there called as the DRL, which combines the reinforcement with the deep learning. We are going to cover the part related to a deep learning. Neural networks are there. So if the structure is like this, neurons are there, 4 input, again hidden, again output, that type of structure is there, then it will have a deep learning thing, right? So it will combine the like reinforcement learning with a deep learning or neural network, where it will have a DQN, A3C or PP or SSE models are there. So these are the like names of the model that we are going to use. In a general, we can like remember it's just a reinforcement, or you can see model based reinforcement or model free reinforcement. Okay, so these are some of the types for reinforcement. So this type of some equation is formed there, right? So in Q learning, the model is, or like Q learning is a model that is a free reinforcement learning algorithm is there. Which type of Q learning is there? Model of free reinforcement learning, which is used to learn the best action that agent is taking to maximize the cumulative rewards. So key components in this are like agent, environment, state, action, reward, and Q value. This Q value is defining the quality of taking action in a state. Quality, that means maximize the reward or minimize the reward. Okay, so this is how it will work. Q, some current state and action value is there, current Q value, quality value, and it will have some other parameters as well. Suppose learning rate alpha is the reward that received, we will give it as like a alpha, gamma, and some S dash next function is there. So maximum among these value will be a maximum future reward. So this is how it will work in a backend. No need to like go with this formula or remember this formula. Just we need to understand how it is working. So ultimate aim is to maximize the whatever rewards we are having. Output will be based on the like Q table it is forming. You will see how it is formed in the case of at the time of implementation. So this Q table stores the value for the state action pairs, which will help the agent to select the best action. Higher Q values indicate better expected rewards. Higher Q values indicate better expected rewards. So agent improves the decision making over episodes, right? So the agent learns through the repeated interactions with the environment, where each episode improves the agent's experiment. Each episode improves the agent's experiment. For a wrong action decreases over the time, and better actions are selected more frequently. So better actions should be selected more frequently. Higher reward indicates the better policy, and that will be followed through this trial and error method. So after trial and error, which policy is followed? Better policy that is followed, which rewards act as a feedback for the agent. Higher rewards means better decisions. The goal is to learn the optimal policy, right? So pi of S is equal to A. Some equations will be used there, and this output learning will be there. If it is a type of a deep learning, deep reinforcement learning, DRL, free. So in that deep reinforcement learning, which combines the reinforcement learning and deep neural network. So right now we are not having idea about this neural network. So it will just combine the reinforcement with this reinforcement learning. It uses the deep neural network. So sometimes people are asking what is a DNN. So it's just a deep neural network, which is a combination of reinforcement plus deep learning, which learns the optimal actions in a complex environment with a large state and action spaces. So how it works? It observes the state, that is a current state, ST. Neural network process the state, age correct action, that is AT, and environment returns the reward RT at that particular time. T is that particular timestamp value. So agent improves over time over here. Agent, that is a action, reward, this continuous action will be there in that particular state neural network. So it will have some Q values, quality value there. So neural network approximate the action value function. There is Q, SA, and theta. So where theta is like network parameter, different parameters will be there. These neurons define the parameters over there. After completing the neural network model, you will have like idea about this, right? So for key components of deep reinforcement learning or DRL will be like agent learns and take actions based on the policy. Environment provide the states and rewards in a response to action, where neural network approximate the value or a policy function from the data. And this reward signal is nothing but feedback from the environment to guide the learning. So policy is defined by the strategy for selecting an action like that. So popular DRL networks, we just see this part, right? Deep Q network, call it network is there, policy gradient, action critic, PPO, proximal policy optimization, A3C, asynchronous advantage, actor critic, like that. So in gaming, in robotics, in self-driving car, in healthcare for the treatment and optimization, you can find the application. So these things are there. Applications for reinforcement are like, you will find a number of applications there. In robotics and self-driving cars, like people are more looking for it, right? So decision making in a dynamic environment, lane changing, parking, traffic navigation, collision avoidance, there it is used. In like gaming and AI, it is used. Recommendation system, like provide the personalized recommendation which improves the user engagement there to increase the watch time for the particular OTT, like that. For healthcare, like ICU monitoring, treatment planning, like that. In finance and trading, you can find its application. Industrial automation is also there. Smart energy systems, like reduce the energy consumption, in that also you will find it. For chatbots, virtual assistants, text summarization, dialogue system, you will find its application. Education and personalized learning, in education and personal learning also, adaptive learning platforms, you will find application for the reinforcement learning, like that. Okay, so this is how it will work. If we talk about the like advantages for this reinforcement learning, it will have applications which will learn through the experience. Okay, advantage is it is learning through the experience. So adaptation is there. So through the trial and error, it learns interacting with the environment. No need for the labeled training data over there, and which improves the performance over a trial and error, through the trial and error, which handles the like maximum or like complex decision making is there. So it solves the complex problems, which is very useful in a dynamic and uncertain environment. In robotics, in self-driving cars, you will find applications. Continuous learning is there, where results are continuously improved. Okay, so this is how it is working. Optimization of a long-term rewards are there. It works with human and supervision, effective for the sequential problem, supports the like real-time decision making there, and which improves the automation. So these things are there. These are some of the pros for the reinforcement learning. And if we talk about the like limitations of reinforcement learning, sample inefficiency there, like if sufficient data is not there, reinforcement learning required large number of interactions. Okay, so for learning, it should have like more data, not efficient when real world interaction are expensive. Okay, so most of the time we need to work with the prototype first, and then we are going for the actual implementation. High computational cost is there, obviously. To train the reinforcement learning agent, it can be a computationally intensive, computationally challenging, which require high memory and processing power, not suitable for a device with limited resources. So these are some of the limitations or cons for it. Sensitive to hyperparameters, depend heavily on the hyperparameter tuning, requires extensive trial and error. So exploration and exploitation, both the things are there. Right? It is difficult to balance between the exploration, that is trying a new action, and exploitation, like using a known based action. So new thing as well, like new thing balance with the available one. So poor balance can lead to a suboptimal policies. Again, sparse reward problem is there. In many environment, you can find rewards are like rare or delayed. So we need to like deal with this, which is very hard for the agent to understand which action should be taken and which action will give you the good results. So these are some of the disadvantages or like limitations there, and are not guaranteed to find optimal solution. It is not that always you will get correct solution there, right? So it's difficult to handle the large or like continuous state spaces, and environment dependency is there. So this reinforcement learning agent are highly depend on the environment. Poor generalization across the changes. Okay, these things are there in a cons. So all these things are related to a like reinforcement theoretical part. Now we will move to the implementation part. But before that, do you have any doubt related to any term? I know these some of the terms are new to you, right? Because generally we are covering supervised. Like honestly, I'm saying this. We are just going with a supervised and unsupervised. That is sufficient. In machine learning, we are just focusing on these two things. This time I have included this topic, reinforcement learning, in first time. for the detecting. Okay. So I know like not 100% sure, but some of the portion you are like okay with. Is it okay, Prema, Bhavya?
Yes, sir.
Or at least you have idea how it is working, how it will work.
Yes, sir.
Okay.
Yes.
So if we like see the implementation part, so we are going to use it for the like implementation of the reinforcement learning for optimizing energy design. Suppose we are having two use cases over here. We are just trying to optimize the energy consumption. If there is a low load for the machine, so power should be less. If there is a high load on a machine, power should be like increased that way. And second use case that we are going to cover for this, that is a robot movement. How robot will reach its destination with optimized way. Okay, in a less time without wasting or without taking too much resources, or like without creating any clashes, or without obstacle it is reaching there. Okay, so this is how it will work. So what is the idea behind it? We just saw, right? Agent learns the best machine operating mode. What we are going with first, energy consumption optimization using a Q learning. For a particular state, what should be the like energy consumption that we are going to cover in this? So machine operating mode to minimize the energy consumption. Just now we are selecting what are the like their state, action and reward. That is the thing, right? So we need to define a state first. What are the like machine load levels? Low load level, medium load level and high level load, right? Three different loads are there on a machine: low, medium and high. Where if low load is there on a machine, the power should be reduced, right? If state is a low, what should be the action? Reduce the power. If medium load is there, the power should be maintained. If high load is there on a machine, power should be increased. Are you getting this? So for three different states, we should have three different actions. Yes, that should be taken by the agent. What is the agent here? Machine like operating machine will be an agent over here. Is it okay? So we are trying to optimize these things with the help of a Python code. How we will implement this with the help of Python code. But before that, are you okay with the idea, or like what is the like statement over here? So agent should learn the like best machine operating mode to minimize the energy consumption. It should not be like that there is a low load and a machine is working on a highest power. So we are trying to optimize this. Yes.
Yes, sir.
Okay. So first of all, we will import the NumPy as a NP, that is a like numerical Python library. Random we will we will import it in order to create a random numbers, random states. So these two libraries we will use over here. States are defined in a list like a low, medium and high. Again, actions are defined with the reduce, maintain and increase sequentially. For low to reduce a power, medium to maintain a power, with a high load power should be increased. Correct? We are just creating a queue table. So in order to initialize the queue table, how we are initializing? np dot zeros. What is the function of np dot zeros? Yes,
Give 0.
it will create a, like a table with all zeros, and whose length is length of action and length of a state. Whatever actions and states we are defined, so it will create a matrix with 3 by 3. Is it okay?
Yes, sir.
3 by 3 zero matrix, correct?
Yes.
And there are some hyperparameters like alpha, gamma and epsilon that we need to define, and these are like generally taken values. These are assumed one, where alpha is a learning rate, gamma is a like discount factor, which should be a maximum 1. Around 1 value should be, and this should be a less one, like 0.1, 0.2 value is there for epsilon exploration. Okay, so these are the like key things over there in a hyperparameters of reinforcement learning. Okay, so this is how it will work. And we need to define a reward matrix to lower the consumption, which give the higher reward. So we are just giving it reward is equal to np dot array of 5, 2, minus 1, which will have like a low load, 3, 4, 0, which will have a medium load, and minus 2, 2, 5, which will have a high load, like this. So these terms has been taken as a, like in order to maximize the reward. It is not like these values will be there, but I have just taken a reference from somewhere. So it should give you the higher reward. So this reward matrix should be formed most of the times you will find. So these are taken from some reference which will give you the like higher reward. For reinforcement learning, I just search for what can be the values for the reward in a 3x3 matrix. So 5, 2, -1, this 2D matrix is there. And episodes, that means how many numbers it will repeat, how many iterations will be there. So that value is taken as a 1,000 over here, and we have written some code in order to like maximize these rewards and finding the optimum value for the energy consumption. Okay, so for episode, in the range of episode, 1,000 episodes will be there. State equal to random dot ran integer 0 to 2. What is the meaning of a 0 to 2? 0, 1, 2. Correct. Three actions, three things are there. Correct.
3 states.
Random dot ran integer. Then if random dot uniform 0, 1 is less than epsilon, so epsilon, this value we have already defined. Action should be like
Uniform.
random dot uniform, that is 0, 1 value is taken there, right? So that is a function under the what we can say random library, which will give you the some value. That value should be less than epsilon. So we'll see what actually it is giving, right? So we'll try to fetch the value for the random dot uniform first. Random dot uniform 0, 1, right? So floating number it is giving actually in that particular range 0 to 1. We have taken 0.1, I hope, epsilon 0.2. So this uniform value in the range of 0, 1. Just a minute. We'll try this first. Random dot uniform 0, 1. So number will be random is not defined. I hope we need to like call this import a random. Fine. So it will give you the uniform value between 0 to 1. So you will get any value in the range of 0 to 1. So number is randomly selected, randomly selected in the range of 0, 1. Now its value is changing, right? Every time you are executing, so you will get any value in the range of 0 to 1, just like a random integer. But random integer is giving you the integer value. This will give you the decimal point. Okay, so it can include both endpoints. Sometimes it may be a 0 or 1 as well. 0.0 and 1.0, both values are included, but always returning a float value there. Always returning a float value. Okay.
Yes.
As like random dot ran integer give returning you the integer, right? That we have seen already.
Yes, sir.
Random dot random is giving you the 0 to 1 value always, right? So here uniform is used because you can change this 1, 2, right? This way it is used over here 0, 1. Is it okay?
Yes, sir.
So if value that is less than the epsilon, the action should be like random dot rand integer. Anything will be there in the range of 0 to 1. What is the 0 to 1?
Sir,
Yes.
if random dot uniform will give always the value between 0 to 1, then it is always less than epsilon.
No, epsilon is a 0.2.
So it will be always okay, sir. Sorry.
No, not always. It may be 0.44, like 0.30. Yes.
I'm a little bit confused.
And yeah, and action will be, if action is like, if this condition is satisfied, action will be random dot rand integer any one in the 0, 1. If it is not, then action will be numpy dot argmax of a q state. Numpy dot argmax of a q state, that means index of that particular argmax is giving you the index for that particular array, right? How argmax is working? Do you have idea about argmax?
Yes, sir.
Argmax is giving you the on which location, on which index maximum value is there. Max function is returning the maximum value, correct?
Yes, sir.
Max function is returning maximum value, and argmax is returning the index of a maximum value. Yes.
Yes, sir.
Reward is equal to rewards of reward we are already having, and in that state comma action or state of action. So state, suppose 0th state 1 action, so it will be selected this way, like rewards of what action is there and what state is there, 3x3 matrix. Next action will be again random dot rand integer of a 0, 2, and final answer will be like some formula is used over here, q of quality of a state action is equal to Q of a state action plus alpha that is already taken into reward. What reward you have received with this value gamma into np dot maximum of Q next state, Q of next state minus Q of state comma action. So next state that is a next state action that is a current state. And you will get optimized Q table over here with the help of a Q. This Q will give you the Q of state action. This will give you the optimized Q table. So 34, 23, 20. 34, 23, 20. If you observe what is like there 34 plus 23. How much it is? 60, 80. So if you put this in the form of this table, okay, if you put this in the form of a table, so what is there? What are the actions? Those are row wise: low load, medium load, high load, right? Then reduce the power, maintain a power. These are the actions, state versus action. So if a low load is there or a low load, reduce the power. How much is the like probability? Better action is highest value is giving you the better action, right? Highest value is giving you the better action. So for example, I hope it is not working fine as per my increase the power. Okay, fine. So these values are different one, right? I have put this initially. So right now it is not working. So 34, 23, 20, these values are there. So what does it means? If there is a low load, reduce the power. What agent will do? It will reduce the power. If medium, like in this 32, 26, 24. So I hope it will again reduce the power and maintain a power in case of high load. But how it should be? It should be like this: low load, reduce the power. This value should be a maximum. Right now it's not working as per our expectation, right? So if you perform,
Load, we have
so
to increase the power, right?
correct, it should be like this value should be a maximum one. Right now you can see 34 is there, right? For second iteration it is a 34. We'll try one more time, right? So near about like it is giving you right now, like we are selecting randomly, correct? We are working randomly, we are giving these values randomly, zeros, values and all those things. So first thing first, here second and here third, it should work like this. So this will be learned through the trial and error methods, and this algorithm will learn which action saves more energy. So output interpretation is like low load, reduce the power, gives the highest value to save energy, correct? Right? So medium load gives the maintain a power is the best, high load increase the power, that is a best thing. So we are like doing this, printing a best policy for I in a range of a length of a state, print state of a I. So that is 0, 1, 2 value will be given, an action of np dot argmax of a q comma I. So index value, and it will give you the maximum values. So best policy is as per our table, as per our table of a Q, best policy is low, reduce the power, medium, reduce the power, and high, maintain a power. These values are given there only, right? So this is how it is working, because for first index it is a maximum value, again first, and for a second maintain a power. Is it okay, guys? I hope you have like at least you get idea how it is working for
Yes,
this
sir.
problem,
But the
both of you.
program is not working correctly, right, sir?
Right now it's not like as per our expectation.
Yes, sir.
Actually it should be like a low reduce, medium maintain, and high increase.
It will be. It is doing like the reverse action.
Not a reverse, but these two things are not working fine. Low reduce is fine, right? When there
Okay.
is a low load, reduce the power. When there is a medium load, maintain a power. When there is a high load, increase the power. These are the states there, right?
Yes.
Is it okay?
Yes, sir.
So this policy, or how if this policy is defined, it will help us to minimize the energy consumption while maintaining the system performance. Is it okay?
Yes, sir.
Is it okay for the like energy consumption? Finding the optimum value for the, yes,
In Q, we are getting the output, no, sir.
correct, Q table,
Q
Q
table.
table.
What we are getting, sir, the values are the power values. Is the power values are power values? Sir?
So these are the power values
Yes.
column wise,
Okay.
okay, and row wise we are having the load values, state values.
Yes.
and actions are defined with these numbers. What should be the action? The maximum number is defining the action there.
Yes.
In these, among these three, what is the
Let's look
maximum
at
number
uniform.
that is a defining action?
Yes, sir. Here it's 33. 33 is the maximum of all the values, right, sir?
Correct.
Yeah,
33 is the
but
maximum.
here we
Maximum
have to
of
reduce the power, sir. Then it should be less.
reduced power 33.
The power would be reduced means in numbers it should be less, right, sir? The power value should be.
No, which is like maximum value. That thing will be considered. What is the first index? Reduce the power. What is second index? Maintain a power. It is not a power value. It is a reward value.
Okay, okay, sir. That means the action is
Reduce
performed.
reduce reduce power is having highest reward.
Yes, sir. That means
Maintain power is having yes.
that action is performed perfectly, right, sir?
Correct.
Yes. Okay.
Prema?
Prema is not there in the call, sir, actually.
No?
I think there
Okay.
is having some.
Fine. So is it okay till now?
Yes, sir.
Okay.
Have we initialized some table
Q
value?
table we have initialized with the zeros. 3, 3.
Okay. Okay.
Initialization is np dot of zeros.
Yes.
If we see this, I hope it will work.
Yes, sir. I didn't remember what we have initialized with that, sir.
It's a like Q table first with the zeros value. Array of a 3 by 3. Length of a state, length of a action.
Yes.
Done?
Yes, sir.
Same thing we can implement for the robot movement. Okay. In order to finding the robot shortest path to goal without having the clashes or just avoiding the obstacles there. So same thing we will do over here. We are just importing the time and matplotlib over here in order to like plot the graph. So it will show us the how robot is moving. Same again. For the like movement, I'm just taking the grid size of a 5 by 5, just a cross of a 5 cross 5, and goal is 4 comma 4. So 0, 1, 2, 3, 4. These values will be there just like this. You can get idea. Like 0, 1, 2, 3, 4 values. Again 0, 1, 2, 3, 4. This first box will give you the like on X side 0, 0, comma 1, 4 again. Column wise again same. So what is a goal over here? Starting from 0 it should reach to 4 by 4 without having any obstacle or like any obstacle eating. Okay. So this is how it should work. So that we are trying to implement. Same again, same code is there. Same type of code is there. Same type of code is there. And what we are defining over here, grid size 5, goal is 4 by 4 and start is a 0, comma 0, just the coordinates there, right? Yes. Bhavya?
Yes, sir.
Okay. And Q,
Yes,
we have just initialized np.0 grid size of and grid size comma grid size. So 5 comma 5 and 4 boxes should be there, right? Like it will be a 5 cross 5 there. Again, actions will be for right action, it should move to the 0, comma 1. For left action, it should move to the 0, minus 1, correct? X axis, X minus and positive will be there. For up and down, it is like defined with the help of 1 and 0 and minus 1.
sir, for upper,
Zero.
it will be 1 and 0 and.
No. Here it is like this 0. So for 0, 1, 2, 3, downward side positive values are there. That's why it is taken like this.
Okay.
If you are taking like minus 1, 0, so graph will be like different one, inverted one. Don't worry, it will work.
Okay.
If you are like going with our traditional way, it will work. So it's completely fine.
Okay.
Right? Again, same alpha, gamma, epsilon, if we stored values. We are just defining the function over here. Some changes will be there. Defining reward function and parameter is just a state. If state equal to goal, return 100 and else return a minus 1. So just what something is defined in order to like store this value. If that particular state is equal to goal, just return it's completely fine, 100%, right? And if it not, there is something wrong. Okay, for training it, we are just training it with the help of episodes. So range for the episode we are taken at 300. State equal to first state will be a start point only 0, 0. While state is not equal to a goal. If state is not equal to goal, so it will go to the goal point, right? It should reach to the goal at the end, if random dot uniform less than uniform, same again. Action should be instead of a 0 to 2. What is there? 0 to 3, because 4 actions are there, right? 4 places we have to move over here. Is it okay?
Yes, sir.
Correct. Else action equal to argmax of a q state 1, same. Move equal to actions of action. New state equal to. New state will be a maximum of a 0, comma minimum of a grid size minus 1 of a state, and move to the 0th position and move to the 1 position, right? So this is just defined with the help of this grid. In order to move to the next position, R is equal to just
Reward.
instance there, reward equal to new state, and same formula is there again. 0 state of a 0, state of a 1, and action q state of a 0 1 action alpha into r, that is a reward only. We have defined in last code, we have defined with the help of reward there. State equal to new state. If we are printing it, so in order to print it, we are just using a plt.ion, that is just a function in a plt. State equal to start fig comma axis, figure comma axis, plt dot subplot is there. Why subplot? Different boxes are there, and it is given with the help of a different colors, right? For I in a range of a grid size, for j in a range of a grid size. Two for loops are used over here. Just a nested for loop is there. Ax dot text j comma I. So f literal is used in a print statement. I comma j 0 comma 1 it will work. H is equal to center, right? In a center you will have this value 0 comma 1, I comma j. Okay, I comma j, first row first column, first row second column, first row third column, like that, right? It's the value will be at center. Vi equal to again center. Color is a black. In black color you will see these letters. Okay, access equal to set title robot navigation, just a title for that graph. Plt dot pause 0.8, like some size will be there, and action argmax of these values 0 comma 1. Move equal to actions should be selected from action that particular array, and state we have already defined there. If we are plotting it, it should work like this. Robot reached golden lines are there, and it will work in a grid size, right? These some values are defined over there. 4 comma 4 will be your destination there, right? So it will find some path and it will try to reach there. So obviously it is a little bit hard to analyze the things or visualize the things, but this is how it will work in a reinforcement. Okay, in a reinforcement it will learn through the trial and error. So we just applied reinforcement over here to optimize the energy designs and robot navigation. Two things we discussed over here to optimize the energy consumption and robot navigation or robot path finding. So model learn optimal actions through the rewards and penalties to minimize the energy consumption, and which ultimately improving the movement efficiency for the robot. So it successfully identified the efficient path and control strategies, and overall reinforcement learning proved that effective for the solving complex optimization problem in a dynamic environment, right? So if we are trying it in a prototype thing, so obviously it will work on the large scale. Okay, so this is how it is working for the reinforcement learning. People are not more not asking that much question in the interview, but there are some use cases those are going right now based on this. Okay, so at least we should have a idea about the key components, how it is working, what is the basic principle behind it. So those things we should know. So that's all, Bhavya.
Yes, sir.
Thank you.
Thank you, sir. So tomorrow.